Hello, everyone. Welcome to our December 2021 edition of Astronomy on Tap Baton Rouge. This is the last show of the year. We're still online for now, obviously, but we're currently monitoring the Omicron situation in Baton Rouge before we commit to returning to any in-person shows. So stay up to date on our social media and we'll keep you posted if we do return to in-person at any time. But this month, we're discussing two really important topics with some speakers from out of town. So before we get started with those talks, here are the usual ground rules. They're the same every time, but the first one is be considerate in the chat. We've never had issues, but always worth saying. Number two, feel free to ask any questions that you have for our speakers at any point during the talk. You can drop those into the chat on YouTube and I will field them to the speaker after the talk is over. Number three, please consider donating to our show. This is what lets us keep actually doing the show after all this time. We aren't currently able to use our Venmo, as was true last month as well. So we only have PayPal. However, as per usual, we do like to add competition to our donations. And this month we want to know, which of the two famous space telescopes do you think looks cooler? Hubble Space Telescope or the hopefully soon to be launched James Webb Telescope? If you choose to make a donation, please write your answer in the memo section so that we can make sure your vote actually counts. And the fourth and final thing, please make sure to like this video if you're watching and subscribe to our YouTube channel, because both of those things help us out a whole lot and they push us to more viewers so that more people get to see all of our wonderful talks. So without further ado, let's move right on to today's talk. Our first speaker today is a fifth-year graduate student at Texas A&M University. In his free time, he plays Dungeons & Dragons, he cooks delicious vegan meals, and he plays Nintendo Switch. Normally, he studies the dynamics of Milky Way satellites, but today he's here to tell us about the 2020 Astronomy Decadal Survey and what that means for all of us professional astronomers. So please welcome Alex Riley.
Okay, I'm just gonna get us rolling here. Okay, cool. So I should be sharing my screen and everything should be going right now. So I'm here to talk about essentially what's going to be the next 10 years that have been planned out first for the field of astronomy. This is big dreams, big telescopes, and all that fun jazz. So kind of the first thing that I want to start off with is if you kind of were to poll any astronomer off the street. And ask them, what do you want to know? What are you studying? What questions you want to answer? You'll get a wide variety of answers here. Some people will say, oh, I want to know what the first stars, galaxies, or black holes were like. Others will say, I want to understand the nature of dark matter or dark energy, some of these like fundamental aspects of how our universe works. And even yet others will say, are we alone? What does it take to kind of create life in terms of astronomical settings and that type of thing? So all of these questions are obviously like important and we want to answer them, but each of them actually requires different instruments and different capabilities. So in order to kind of navigate all that and come up with a hierarchy of, okay, what projects get funded, we need to kind of make sort of like a collective decision-making process. And the way we do that, I don't know what this is messing up right now. So how do we decide which of these questions we want to work on or prioritize, what gets built? And the answer is this thing called the Decadal Survey. So this is a survey that happens every 10 years that's run by the National Academies of Science, Engineering, and Medicine. This most recent one just concluded a couple of weeks ago, something like that. And it was called Astro 2020. And so we're going to be discussing kind of what was in Astro 2020, what the process was like, and what the next 10 years of astronomy is going to be like. So really quickly, kind of Astro 2020 by the numbers here. So this was a massive undertaking. It was led by these two people in the top corner, Fiona Harrison and Rob Kennicott, who's incidentally also a professor at Texas A&M, where I am at. His office is 4 doors down from mine, so that's fun. and this was a massive undertaking. So ultimately, in the kind of early scope, where the committee that was set up to kind of run the decadal survey asks for input from the community. So any astronomer can submit what's called a white paper, and this can be either advocating for a specific telescope to study a particular topic, some aspect of the field that you want improved, anything like that. So overall, 860 of those white papers were submitted. 573 of those were kind of science-based, and then others were kind of how do we improve the structures of how we do astronomy in the United States. The final report was 614 pages. I did not read all 614 pages, so don't ask me what's in all 614 pages. This is just a nice brief summary. But obviously, like this massive undertaking. Overall, there were 13 panels, each one tasked with a different science topic, or there's one panel on just the state of the profession in general. And then in addition to those 13 panels, there was one overarching 20-member kind of steering committee. And that was what was chaired by Fiona and Rob. And so out of like past decadals have emerged like basically the household names of instruments and observatories in astronomy. So in the 1970 decadal was how we got the Hubble Space Telescope and the VLA. 1980 gave us the Chandra X-ray Observatory. 2000 was actually the decadal where the JWST was formed. We'll hear about JWST in the next talk. And the 2010 decadal survey gave us what's now known as the Roman Space Telescope, formerly known as WFIRST, and the Rubin Observatory, formerly known as LSST. So these are big, like massive undertakings. And one of the primary goals is to come up with a ranked list of observatories or missions that should be funded. The most important of which being these flagship NASA missions, examples of which we just saw. And so of these observatories that were proposed for this most recent round, Astro 2020, there are actually 4 proposals. So LYNX, which is an X-ray telescope, HabEx, which is focused particularly on exoplanets, habitable worlds, LUVOIR, which stands for the Large Ultraviolet Optical Infrared Telescope, and then finally Origins. So all 4 of these went through a pretty extensive proposal process, and one of them was chosen, and we'll find out which one later. So really quickly, I want to talk about like who this is for, who the decadal is meant for. So in addition to just setting priorities for the next 10 years in astronomy, the types of questions that astronomers are interested in. This is the main audience for the decadal. There's kind of 2 buckets. So there's funding agencies. So the NSF and NASA primarily, also a little bit the Department of Energy, are actually the government agencies that are going to like the budget for these telescopes and funding the science are going to come from these funding agencies. So this sets the priority. This tells those agencies, here is what should be built. And then obviously this is also kind of geared towards Congress, also the Office of Management and Budget in the executive branch, because these are the people who write the budgets for these funding agencies. And if we're advocating for a particularly large and expensive telescope like JWST was, that involves getting allocated funding from Congress. So, there's actually a lot of lobbying that astronomers do. So the AAS, the Professional Society for Astronomers, and lots of other people kind of gather, once a year, use the decadal as kind of their primary tool for advocating for science funding in astronomy. So this is a picture of some astronomers that actually visited Capitol Hill and talked to a whole bunch of congressional members. This one is also at Texas A&M's Arnie Kinchadi. Just a shout out to my 1st through 3rd year office mate. Okay, so I've been talking for a while. What actually was in the decadal in Astro 2020? So there were three major science themes that were kind of overarching, kind of coloring everything that was recommended. So the first one is called Pathways to Habitable Worlds. That's essentially looking for exoplanets, characterizing their atmospheres, and trying to figure out the origin pathways for life as it relates to astronomy. The second one was New Windows on the Dynamic Universe. So this is using things like the latest and greatest radio observatories to take a picture of the event horizon of a telescope, like we're seeing in that picture there. Or it could be things like incorporating the gravitational waves of two black holes merging and what that tells us about the universe. The third one is unveiling the drivers of galaxy growth. So basically, how do galaxies form, and how is that connected to the dark matter that tells you where those galaxies form, and the gas that is around those galaxies and actually forms the stars. So we're back to these four proposed missions. So the fun answer to, hey, which telescope was picked, was actually kind of a mixture between two of these. Essentially what the Decadal Committee did is they took a look at these, took the best aspects of two of them, when two telescopes kind of, meet their eyes, fall in love, they can perhaps form a new baby telescope, and that telescope is this next flagship mission. So unfortunately, this doesn't have a name associated with it yet, so I can't call it anything useful. But you can kind of think of it as an ultra Hubble. So the way it was built is kind of an all-purpose infrared optical ultraviolet observatory with about a 6 meter mirror, which is slightly smaller than the mirrors that were proposed in some of these large massive missions. And that was basically just like a technical, we don't think we can build a telescope that large and put it in space yet. This Ultra Hubble is going to have 250% the resolution and 6 times the light gathering power of present day Hubble. And the plan is to have it to launch by 2040 and have it cost about $11 billion, which is a large chunk of money, but kind of comparable to telescopes in the past if you kind of drag that cost forwards to $20-40. It's kind of a steal. The terrifying aspect of this, at least for astronomers of my generation, was nicely summed up in this tweet, realizing that this massive observatory is going to be launched in our 50s. If you're like a 20 to 25-year-old graduate student, which is something. And then another aspect of this, so you'll notice that the wavelengths that this observatory covers is infrared, optical, ultraviolet. And you might remember that there was a proposed telescope called LUVOIR, the Large Ultraviolet Optical Infrared Telescope. And so this led to, by far and away, the best tweet I've had in years. It's only a LUVOIR if it's from the Loire Valley in France. Otherwise, it's just a sparkling large infrared optical ultraviolet space telescope. So that felt good to have happen. In addition to proposing this kind of ultra Hubble, there was also this thing called the Mission Technology and Maturation Program. So the idea here is that flagships take about 20 years, and often they're greenlit with kind of unproven tech. This is part of why there were, cost overruns and continuous delays for telescopes in the past. This was true for Hubble. It's true for JWST. And so to kind of fix this, and again, leads to delays and cost overruns. So starting now, in order to fix this, the technology needs to be proven before you start constructing the telescope. This sounds very obvious to any engineers that I've talked to about this. But yeah, like astronomers really liked to greenlight telescopes before we knew we could build them. So now we're going to fix that. So one aspect of this, in order to not just have large gaps where there's only like one or two observatories going at once, we're going to start designing the next flagship during the construction of the current flagship. So there will be kind of an overlap in this planning, construction, launch, and operation stage. Okay, so in addition to this flagship space telescope mission, you also have a lot of other facilities that were kind of greenlit and approved. So this includes literally the biggest telescopes ever. So there's kind of two proposed telescopes. They're both shown kind of on the right here. And collectively they're going to be referred to as the ELT project. So extremely large telescope. We're great at naming stuff. And so this is kind of combining the Giant Magellan Telescope, GMT, or the 30-meter telescope, TMT. So importantly, we'll get to that. So currently, kind of world-class ground-based mirrors are like 8 to 12 meters in size, and these will substantially increase that, somewhere between 25 to 40 meters. So something like 100 times the light gathering power. The decadal survey recommends that the NSF funds either 25% of both observatories or 50% of one observatory, because we're not quite sure which of these or both are actually going to get built. There are some problems there. In total, this will cost about $1.6 billion either way. This will catch the US up to Europe in terms of building extremely large telescopes. They're already going with the European EELT. But there are kind of considerable hurdles to go. One telescope may or may not have the ability to build on the mountain that they want to build it on. And both telescopes are having issues gathering all the funding necessary to build them. But the decadal was very clear that the US should build an ELT program, and it either should be GMT or TMT or both. And they were clear about how much of that funding should be put in. There are a whole bunch of other next generation recommendations. The CMB S4 is kind of the next generation cosmic microwave background experiment. So we had WMAP and Planck. Now we're going to have a better in every way instrument that will help us detect the imprints of the very early universe. There's going to be a next generation VLA, which will have the resolution to see planet formation happening in action, which is awesome. There's going to be a second generation of a observatory called IceCube, which is essentially a whole bunch of particle physics detectors that use the ice sheets in the South Pole to detect very high energy particles, neutrinos, that come from extreme events like the most massive black holes and that type of thing. And we'll also have upgrades for LIGO and tech development for LIGO successors. So LIGO is these observatories that have detected gravitational waves for the first time. And so this is going to build up on that. There's a whole bunch of other stuff that I just don't have time to get into, and it's all summarized kind of on this slide. In addition to kind of setting science goals and all of these different instruments and observatories that are going to be built, the decadal talked plenty about ways to improve the way that science is done and the people who are doing it. So expanding grants, diversifying the science workforce, making sure that there's money for having your data be open and available for anybody to use. All of these things are kind of baked into this decadal. And this is also summarized by a great tweet here that basically, like, if you're just taking one quick glance at Astro 2020, it's basically like, let's do it all. It's all great. Let's go. So if you're wondering, geez, Alex, all that sounds pretty expensive. The first answer is, yeah, you're right. It is a lot of money, but in the grand scheme of things, it's actually not too bad. So this was compiled by an astronomer on Twitter, Grant Tremblay. And if you kind of compare, earlier we were talking about Lynx and Origins, these kind of proposed telescopes, and LUVOIR is also in here, to other line items in the U.S. federal government's budget. You kind of get some interesting comparisons here, like the amount in $100 bills that the U.S. military lost, LOL, oops, in Afghanistan in 2012 is larger than the estimated cost of Origins, and also the Ultra Hubble that actually got recommended from the decadal. And the cost of air conditioning U.S. military bases in Iraq and Afghanistan in 2011 was $20 billion. So if you kind of add up all the things in the decadal, the scientific advancements that we'll get from astronomy are quite comparable to these other things that the government has decided we want to fund. And that is completely dwarfed by other things if you start looking at, things like the annual Pentagon budget, wink, wink, nudge, nudge. So I would kind of argue that, it's really just time to make astronomers like work together to make these dreams a reality. This is a very achievable roadmap that the Decadal Survey has made for us. And I think that if we work towards, if we all band together and advocate for what the Decadal has recommended, I think we can actually do this. I think we can do all these really great things. So these are the credits to not get me in trouble for using the slide template that I'm using. So that's there. And that's all I've got. I'll take any questions.
Cool, thank you. If you want to unshare your screen, I can get you some questions. One thing that I thought was funny was that you have a picture of Erin in your slides. I don't know if you noticed that.
Oh, I do?
Yeah.
I didn't even...
All the astronomers on Capitol Hill, she's definitely in that.
Oh my gosh, okay.
Anyways.
Great. I didn't even realize, oh my gosh.
So while I let all of the questions sort of filter into the chat, I get the lovely honor of asking you the first questions. Mm-hmm. And since Astronomy on Tap it's about the science, but it's also about the astronomers, the scientists. And so I want to ask you a couple questions about you. So the first one I want to ask you is, what are your hobbies outside of astronomy?
Yeah, so I play a lot of like tabletop RPGs, so things like Dungeons and Dragons. My best friend and wife actually have kind of a small business that's in the RPG world, and so we've played other games besides those ones. I play a lot of Switch games, a lot of Pokemon recently, and I do a lot of cooking, so trying out new recipes, that type of thing.
All right. What does a typical day of work look like for you, like as an astronomer?
Recently, it's been submitting a lot of job applications because that's what I'm trying to do after I graduate.
Okay, same.
When I'm not doing that, a lot of it is kind of doing research. Mainly, I do like calculations on my computer and using simulation data. So looking into that. And I also have a lot of meetings about that science. So lots of in-person meetings too, and also lots of telecons that are on Zoom, because we have these very like large international collaborations that I'm a part of. So that's also a part of my day.
Okay. And then what got you into astronomy, like back in the day?
That's a great question. The story that my mom likes to tell is that I ended up just kind of reading a lot of books that were written kind of like pop sci books about kind of black holes and that type of thing. And then where I think so she thinks it started there. Where I put the starting point is that I actually had a really great high school physics teacher, and he sort of was able to explain physics in a way that made it very interesting. And then when I was looking at like things that I could do with physics, astronomy was one thing that popped up and sounded cool. So it kind of went from there.
Yeah, I like that there's two different answers. Okay, and then the last question that I have about you before we get into some science is, what is your favorite Pokemon?
Yeah, I was thinking a lot about this, and I actually think that it's still Chimchar.
That's okay.
Yeah, because Chimchar was literally my first Pokemon ever. And so, yeah.
That's from Diamond, right? So I guess you're excited to have that.
I am, yeah. No, that was actually the Nintendo DS was my first video game console that like my parents bought me, and Diamond was the first game that I played on it. So like all like the nostalgia factor for like Brilliant Diamond that just came out was like through the roof. They took my money right away.
Of course, they took a lot of people's money.
Yeah.
Okay, so the first science question I wanted to ask was, what did you feel like was the most important like takeaway from the decadal survey, especially as someone whose career is very much going to be impacted by the contents of the decadal survey?
Yeah. So there's a couple ways that I can answer that. I think the broad takeaway that there was a lot of fear that the cost overruns for JWST would make the community pretty scared for putting forward like a really big, ambitious mission. Mm-hmm. And we still went big anyways, which I think was the right move. So that there was also a really big focus on kind of improving the situations for people who are working in this field. So things like how to be more equitable in increasing faculty diversity, making graduate admissions processes easier, and just kind of making science like a more inclusive environment. Because they make this point very explicitly that the science that we can do is really driven by the scientists themselves. And that was nice to read over and appreciate.
Yeah. All right. And our first question from the audience is from Christine Newman. And she asks, are there enough students headed towards STEM to manage the workers that will be needed to maintain all of these projects?
Yeah, that's a great question. I think so. So I think that as long as the suggestions from the decadal that talk about, in addition to building these things, you also need to fund the scientists who are going to do like the data analysis and all of that. As long as those recommendations are followed, I think we'll be okay.
All right. Allie Chris, one of our streamers, asks, which proposed telescope are you most excited about?
Yeah. So I was really nervous about what they would do for the kind of US Extremely Large Telescope program, ELT program. And I think they mostly made the right calls. So because there was a world where the decadal just says, yeah, these two telescopes don't have their act together. We don't recommend funding either of them. And that would have been really bad for especially like my science field in general, where you really need a really big telescope to study the faintest things, the faintest galaxies. So I'm really glad that they said, there's stuff to iron out, but there needs to be a US ELT program.
Right. Okay. And then another question we have from the audience is from Fallon Franson, and they ask, are there any decadal disappointments or your personal feelings of disappointment?
Yeah. So I was thinking a lot about this, and I was kind of ingesting, what everyone on Twitter was saying. In the broad takeaway is kind of no. Pretty much every subfield found something in this decadal that they were kind of happy about. the I don't know if it's just because I'm tuned into kind of what people in my particular subfield are saying. Some of them were a little disappointed in how much mentions of like we need to understand what dark matter is, and the best way to do that, some people would argue, is looking at like the Milky Way very nearby. Some of those people who work on that were a little disappointed at not getting mentioned as much as they wanted. But then I've talked to kind of more senior members in this field, and they're kind of like, yeah, this is kind of, things, don't be too worried about how many mentions that we got explicitly. So after talking to them, I think pretty much everyone is okay, more or less okay with what happened.
Okay. I actually wanted to jump off of that just a little bit. I felt like from your summary, it seemed like the things that were getting brought up in the decadal survey are things that are really hot in the field right now. So things like exoplanets, galaxies, galaxy dynamics, things like that. Do you think that idea is reflected in some of like the earlier decadal surveys as well? Like, have you looked into any of that as well?
Like in terms of what science they were recommending at that point?
Yeah. If it was like reflective of what was going on at the time, or if it was, different.
Yeah. So I haven't read any decadals. I haven't read any old decadals. I barely read this summaries of this one. But I will say that like especially more recently, there's been a lot of push to include all of this community feedback. Like what the decadal starts off with is you form kind of the steering committee of like the main committee of 20 people, and then they say, okay, astronomy community, give us all of your suggestions for what you want in here, and then something pretty much needs to be in those white papers in order for the decadal to even really consider it. And so, yeah, that's something that I didn't quite appreciate until I heard Rob, who was one of the professors who led the decadal. We were just chatting about this talk actually, and he was like, yeah, we really took what the community said to heart and tried to synthesize everything that was in there. And so I think just from that perspective, it'll be kind of what's hot in the field at that time.
Okay. I believe that is all the questions that we have time for right now. But if you are on the YouTube stream and anyone else has more questions, I'm sure you would be happy to answer in the chat, ?
Yeah, for sure.
Okay. So with that, we're going to take an intermission. Before we break for intermission, I would like to humbly ask you once again to consider donating to our PayPal. And if you do, make sure that in the comments, you let us know your answer to this month's tip war. And just to refresh, this month we're asking you, which of the famous space telescopes do you think looks cooler, the Hubble Space Telescope or the hopefully soon to be launched James Webb Space Telescope? So let us know in the comments of your donation. And I will see you back here at 7:40 my time. Hello, everyone. Welcome back to the second half of Astronomy on Tap. I'll just go right into introducing our second speaker. So our second speaker today is an exoplanet astronomer at Johns Hopkins Applied Physics Lab. If you follow her on Twitter, then you already know that she's an avid knitter and reader, and she regularly updates us on her cat Button. You can also grab some of her wonderful stickers from her Etsy shop if you're interested. She's here to tell us today about the James Webb Space Telescope that's set to launch next week, hopefully, ? Anyways, here is Dr. Erin May.
Great, thank you so much. Okay, so this is the last in my week-long series of telling everybody about JWST and how exciting the telescope is and some of the great science it's going to do once it launches. So Alex let us all know that JWST was the recommended telescope from the 2000 decadal. And here we are almost 22 years later at this point, hoping for a successful launch soon. And I'll let you know an update on that at the end for when that's supposed to happen. But yeah, so I'm an observational astrophysicist. So I use some of the world's most powerful telescopes, both on the ground and in space, to study exoplanets. And our goal is to answer the question, are we alone? There's a lot of steps that it's going to take before we get to the point of being able to answer the question, are we alone? And JWST is one of those important steps. So I'm going to focus mostly on this telescope, and I'll tell you a little bit at the end about how it's going to help us answer this question about, are we alone? But I want to start with a brief history of NASA space telescopes. And I say brief because this could be a whole hour-long seminar on itself. And then I'm limiting myself to NASA here because otherwise there's just way too much information to talk about. These space telescopes have been around for quite a while now, and there's been so many of them, and they've all done such amazing things. So 1968 was NASA's first successful space telescope. This observed in the ultraviolet, and that is the type of radiation from the sun that makes us burn. So it's just a different type of light. It's not something we can see with our eyes, but it's very useful for studying different types of astronomical objects. So 10 years later, in 1978 was when funding was first approved for Hubble. So people were very ambitious very early on about wanting to get these amazing telescopes into space to get above some of the complications of Earth's atmosphere. So 5 years later was when they originally planned to launch Hubble in 1983. So they thought it's only going to take us 5 years to build Hubble and launch it. So that may have been a little bit ambitious. So if you think we've been ambitious with JWST, that's not new. It's been an ongoing problem for us astronomers. So originally supposed to launch in 1983. It wasn't that much later that it was actually done, but it didn't end up launching until 1990 because of some issues with the space shuttle primarily. They wanted to make sure that, one, it was safe to launch the astronauts on the space shuttle who were going to put Hubble into space, but also that it was safe to launch Hubble. So it was about a 7-year delay from the original launch date. Hubble got up there. Famous story, Hubble needed glasses when it got into space. There were some issues with the mirror, and we were able to send the space shuttle up to fix it, luckily. And then through the years, we were also able to upgrade Hubble. So it's been one of the great reasons or great results of the fact that Hubble orbits so close to Earth and that we had such an amazing shuttle program for so long. But once astronomers got Hubble up there operating, we didn't stop there. We immediately started thinking about what's next. So 1996 was when development for JWST begins. And at that point, it's just laying out a list of what do we want in our next giant space telescope? What do we want it to look at? And once we know what we want it to look at, what does that telescope have to look like in order to accomplish those goals? So it's kind of where we're at with the concepts that Alex mentioned, LUVAR and HABEX and origins and links. We're at that development stage where we're laying out the groundwork for what we want in our next space telescope. So the idea for JWST started in 1996. It wasn't actually named that yet. In 2000, Alex mentioned it was selected as the top priority from the 2000 decadals. And because of that, the contract for JWST was awarded in 2003, and that's when the money started coming out, and that's when it started being built. Quick aside away from JWST and HST, I want to mention 2009 was when the Kepler Space Telescope was launched. And this telescope is really the reason why JWST is going to be so amazing for exoplanets, because Kepler has found over half of the exoplanets we know of to date. So without Kepler, we wouldn't be able to be doing any exoplanet work with JWST because we wouldn't have any exoplanets. But shortly thereafter, in 2010, was when we expected JWST to launch. Of course, we all know it did not launch then, but I just want to show that comparison between the fact that there's expected to be a 5-year build date for Hubble, and then they expected a 7-year build date for JWST. There was then a 7-year delay for Hubble from the original planned launch date. And here we are sitting at an 11, nearly 12-year delay for JWST. It's not that far off the mark for other space telescopes. JWST is extremely complicated. We would expect it to take longer than HST, and we want to make sure we get it right before we put it into space. So I have all of those question marks there. I've had them there every time I give them this talk. But sitting here today, I am now at this point almost ready to update the slide to 2022. We shall see. However, once it gets into space, it's going to be amazing. And the first reason it's going to be amazing when it gets into space is the fact that it is the largest space telescope that NASA has ever built and sent into space. Not alone NASA, any space agency on Earth. No one has sent a telescope into space this large before. So this is to scale. Me standing on the bottom left, looking up at, was a Joshua tree. I cropped that out. And now we're looking at the size of the HST, Hubble Space Telescope mirror, about 8 feet in diameter. And then that's compared to the size of JWST, which is about 21 feet in diameter. The mirrors are about 2.5 times larger in total. And that corresponds to something like 7 times the collecting area for the mirrors. So it's huge. And the reason that that collecting area matters so much is the bigger a mirror is, the more light that we can collect. If you collect more light, you can see things that are fainter, and you can also see things that are farther away, and you can see things in more detail. So it's going to let us study a broad range of the universe that we haven't been able to study with HST, and also study things that we've been looking at in even more detail and learn even more about them. So even though Hubble is quite small compared to JWST, it actually weighs twice as much as JWST. Part of that is because of advancements in the mirrors and the technology, but also just, we've gotten a lot better at building space telescopes in the past 30 years. So even though it is so big, it is really not the heaviest thing we've launched into space. Another fun fact, this sun shield, which you'll see in some of the later pictures, is about the size of a tennis court. And the total JWST weighs about the same amount as a school bus. Absolutely huge. And because of how huge it is, we can't launch it in its deployed state. We have to fold it up and shove it inside an Ariane 5 rocket, which was the largest fairing that we had when JWST was being designed. This launch is actually contributed from the European Space Agency. So NASA's getting the launch for free in exchange for giving European scientists some percentage of time on JWST. It's pretty cool when you think about it. This is the tip of the rocket, and you can see JWST folded up and shoved in there, taking up every little bit of space possible. And even though it is pretty cool, the fact that it has to fold up leads to lots of complications. The most obvious of which being that it has to now unfold. So this is a whole long process, and it's going to take several weeks for the telescope to be fully unfolded before anything starts operating. And all of this is going to happen as it's flying out to its orbit at this point in space called L2, which I'll talk about in a little bit. But this GIF is really cool. It's showing some of the most important parts of the unfolding process. The first thing that's going to happen is the arms that hold the sun shield are going to unfold from the telescope, and then the sun shield itself will pull out and tension out and start cooling the telescope and the instruments from the heat of the sun. After that, the mirrors start unfolding. So you have the secondary mirror, which is this, what some people have started calling the selfie stick of the telescope, unfolds, and there's a mirror at the end of that that reflects light back at the telescope. And then the 2 side wings of 6 of the gold panels unfold as well. Once all of that happens and a ton of other small little stuff that you can't see in this, this GIF, if that's all successful, then we can start using JWST after it gets to L2. So a lot of people have asked why we're not orbiting Earth. Why are we sending JWST so far away that we aren't even going to be able to service it or fix it or upgrade it? So L2 is this gravitationally stable point out beyond Earth, and JWST is just going to orbit this point in space. Now, I mentioned that because we had Hubble orbiting Earth, we were able to send this shuttle up to fix it when it was launched with a wonky mirror. And we were also able to send the shuttle up with upgrades to put new instruments on it to keep it being state of the art for the past 30 years. Now, that's great, but there's a couple reasons why orbiting Earth actually isn't the best option for a telescope like JWST. The first of which is the fact that JWST is looking at wavelengths of light that are a little bit further to the red colors. It's called infrared, and that's a type of heat in the universe. Objects in space are generally pretty cold, except for stars. We know those are pretty hot. But planets themselves, even though they're quite a bit colder compared to stars, they do give off heat. And they give off enough heat that if JWST was too close to Earth, it would just be overwhelmed by the heat of the Earth as it orbited it. Another benefit of putting JWST so far away is the fact that we can use it 100% of the time. So HST orbits Earth, and that means half the time it's on the side of the Earth that the sun is on, and it's too bright to observe and we can't use it. So while we've lost the ability to upgrade JWST, we have gained the ability to use it 100% of the time and to look at different things and different parts of the universe that we just can't with HST. And there's going to be a ton of new and exciting science that we can do, even though Webb is so far away. So you can see from this graphic on the bottom that this point L2 is nearly 5 times further away from the Earth than the Moon is, which is a significantly large distance, which means it's going to take a very long time to get there. In total, it takes about a month for JWST to get out to L2. And during that month, there's a lot of stuff happening. So in the first 5.5 days after launch or so is when the sun shield is going to deploy. So that's when those arms unfold and that sun shield pulls out and gets tensioned and starts cooling down the spacecraft. And about 14 days after launch is when those mirrors deploy. Then once it's starting to reach L2, the telescope will be sufficiently cooled down enough that we can turn on the flight software and start controlling the orbit of JWST with that. After another 2 months, we'll turn on the guidance sensor, which has been which is the major contribution from Canada, actually. And then we'll also start turning on some of the first instruments. Now, at this point, the mirrors aren't aligned. And I'm going to talk a little bit about this on the next slide. It's this cool reason why we don't have to worry about JWST needing glasses like HST does. But because it's not aligned, at this point, when we take the first images to make sure everything's working all right, they're going to be blurry. And we're probably not going to have those released to the public. And the point at that point is just to make sure that light is getting into the instruments successfully and everything seems to be working okay. So after 3 months is when we actually start aligning all of the mirrors. So some of these pictures before I showed you have, you can see all these 18 individual hexagons, and each one of them can actually move independently. So what's happening in the top panel is each mirror is getting moved just a little bit until all of those points of light go up and reflect off of the secondary mirror or the selfie stick part, and then go back into the telescope and the instruments on the back side of all of the mirrors. So you can adjust how each mirror is pointing until you make sure all of the light is lining up perfectly and that we have pretty gorgeous images that aren't blurry. I wanted to show this awesome little GIF from LEGO JWST, which is a LEGO version of JWST, which has now been fully funded on LEGO Ideas, and we're really hoping becomes a actual LEGO set. I'm sure LEGO is waiting to see if JWST successfully launches before they commit to it, but I am 100% ready to commit to LEGO JWST. So at these 3 months, the mirrors are aligned, the last instruments start turning on, and we start being able to take the first science quality images. So we can expect, hopefully, sometime next April to get the first beautiful images coming down from JWST. After 6 months, we'll start doing science operations. And at this point, people who have been awarded time on JWST will start getting their data down, and we'll start being able to learn about the universe. Now, there are 4 major science themes from JWST, and this doesn't cover all of the possible science that JWST will achieve, but they're the main goals of the instruments and telescope. So the first one is looking at the first light from the universe. So immediately after the Big Bang, the universe was very dark and it was opaque, and light couldn't travel through the material that made up the universe. But at some point, these stars and galaxies started forming, and as a result, the universe lit up and it became transparent, and light was able to pass through the material in the universe. One of the major things JWST will be doing is searching for these oldest light sources in the universe to learn more about the formation of the universe and the early parts of the universe. The second major science theme is looking at the evolution of galaxies. So galaxies grow and merge over time, and galaxies from the old universe don't look the same as galaxies from the universe nowadays. And part of what JWST will help understand is how galaxies have grown from what they looked like in the early universe to today, so we can understand where our galaxy might go in the future. The third major science theme is looking at the formation of stellar systems. So stars form from these collapsing nebula of cold gas out in space, and the leftover material from that formation forms a disk around the star that later forms planets and everything else in the star system. And what JWST will be able to do is look through the dusty universe at these baby stars and then stars that are older along in the process, and understand how stars grow into what they look like throughout different periods of their lifetime. And then the fourth major science theme is looking at the properties of planetary systems. And this is the one that I am in particular most excited about and will be focusing on with JWST. The point here is to study what planets are made out of, with a goal of looking for habitable environments in the universe. So we'll be able to look at different types of planets and understand what their atmospheres are made out of, what the planet themselves is made out of, and look for planets that have the right conditions to host life. So all of these 4 major science themes are really designed, or JWST is designed around them because they are best studied at infrared light. And I've mentioned this a few times. What I want to talk about is the fact that infrared light is just another type of light. So when we think about light, we think about the things that we can see with our eyes. So this is all of the colors of the rainbow, the visible spectrum that we see when we walk outside or inside, anywhere on our planet. And that's what Hubble primarily observes with, in the visible part that humans can see. But light actually means anything on the electromagnetic spectrum. And this covers things like gamma rays and X-rays that are really high energy, all the way out to radio waves and microwaves, which are really low energy. Infrared light is here just to the red of visible light. It's just a little bit less energetic than visible light with these longer wavelengths. And it's just a type of heat. So anytime you feel heat on your arm, when you're outside, that's infrared light from the sun hitting you. And one of the reasons why infrared light is so special is it helps us see through the dusty regions in space. So what I'm showing you is an image that was taken with the Hubble Space Telescope back in 2001 at visible colors of light, so things that we would see with our eyes. And on the right is an infrared version of that image, taken with a different instrument on Hubble in 2014. And you can see so many more stars deep into this dusty region of space, because this infrared light is passing right through the dust and hitting the telescopes. These dusty regions in space are part of the places that planets or stars form. And so that's one of the reasons why infrared light has been the focus of JWST and what it was built around, to help us see deeper into the universe and see beyond all of the dust out there. Now, in order to see infrared light, the instruments had to be designed in a special way, but also the mirrors had to be designed in a special way because typical mirrors aren't great at reflecting infrared light. And so this is the reason why Hubble or JWST has these gorgeous gold mirrors. So the mirrors are made out of beryllium, which is a very strong and heat-resistant metal, and it's also very light. So that's part of the reason why JWST weighs so little in comparison to HST. And then after these mirrors are made in the beryllium, they're given a thin layer of gold on top because gold is really good at reflecting infrared light. Unfortunately, gold is really bad at reflecting visible light, the stuff we see with our eyes. So that's why JWST won't be observing at these colors of light that we see with our eyes. So what I'm most excited about that JWST is going to be studying are exoplanets. And the first exoplanet was detected actually around the time people started thinking about JWST back in 1995. And since then, we've discovered over 4,000 planets over the past 2.5 decades. And these are everything from the size of Jupiter, orbiting really close to their stars, to Earth-like planets in the habitable zones of their stars. And JWST is going to help us understand what they're made out of so we can look for these habitable environments in the galaxy. The most important thing that JWST is going to be looking at for exoplanets is that it's going to detect atmospheres on terrestrial exoplanets. So as of today, we have not yet detected an atmosphere on a planet that is rocky like Earth. It's because it's really hard to do. They're really small, and these signals are absolutely tiny. But JWST is going to be really staring in on some of these systems and some of these planets, primarily this system called TRAPPIST-1, which has 7 Earth-like planets really close to their star, and 3 or 4 of them are in the habitable zone. So JWST is just going to stare at these planets and build up enough data until we're able to tell if they have an atmosphere around them. Because an atmosphere is one of those things that we know life needs. We need something to breathe. Now, I want to point out real quick that JWST is not actually quite sensitive enough to detect biosignatures, which are these signs that a planet is inhabited, that it actually has life on it. And these are things like specific gases in the atmosphere of the planet. But we are going to be searching for these habitability indicators, these signs that a planet is habitable. So it's just things like, does it have an atmosphere? And what the temperature of the planet is. So the fact that JWST will be able to find which planets have atmospheres is a huge step forward to figuring out which targets are the best ones to look at to find biosignatures on life in the future. And with that, I'm going to suggest you all mark your calendars tentatively for December 24th at 6:20 a.m. Central for you all. But I'm going to put a big question mark on this because tomorrow morning, we are expecting to hear about an update on the fact that there has been a communications issue between the telescope and the rocket. I think that's resolved, but tomorrow they'll tell us how they're going to move forward. It is fueled. It is sitting on top of the rocket. There are stickers on the rocket. There's no turning back, but launch might end up being delayed slightly a little bit. So we will see.
All right, thank you so much. If you want to unshare, then we can get going with some questions. Same deal for you that I had with Alex, where we want to know about you as well as the science that you're doing. So while the questions start filtering in the chat, I have a few questions about you. And the first one I wanted to ask was, I already asked Alex this, but I always find it an interesting question. What does a typical day of work look like for you as an astronomer?
A lot of sitting in front of my computer. I do a lot of data analysis. So right now I'm spending a lot of time with data from the Spitzer Space Telescope, which looked at even longer wavelengths of light, so even further into the infrared, also a type of heat. So just a lot of data processing with various programming languages. Recently, it's been a lot of making slides for outreach talks, because we're all getting excited about JWST and telling the public about JWST. Just, yeah, sitting in front of my computer all day.
Yeah, I feel like a lot of people who maybe don't know that much about astronomers and what they do think we spend a lot of time in front of telescopes, when I always try to tell them we're pretty much just programmers.
Yeah. Back in grad school, I did spend a decent amount of time at some telescopes in Chile, but even when you're at the telescopes, you're just sitting in front of the computers that operate the telescopes. So can't get away from them.
Okay, and then another question about you. What is your favorite part of being an astronomer?
My favorite part is probably talking to the public about the science that we do. It's always so exciting to see how excited the public gets about what we're doing. And I think that's the best part, is that our field is something that everybody can get excited about.
Yeah. What was your path like into astronomy? Like, did you always know that you wanted to do astronomy, or did you start somewhere else?
Yeah, I did not take an astronomy class or know astronomy was a thing that you could do until the end of my sophomore year of undergrad. So I became an astronomy major junior year, and that was the beginning of everything. So this was not a lifetime dream. It was just I kind of stumbled upon it and fell in love.
Yeah, and then you were like, I have to do that.
Yeah.
All right, and then the last question about you personally. What is your favorite Pokemon?
Okay, so I know nothing about Pokemon, absolutely nothing. I was not exposed to Pokemon growing up, and so as a result, I do not pay attention to Pokemon at all. I could not tell you the name of a single Pokemon.
That's okay. That's okay. We support you anyway.
I tried to look up some pink ones because that's my favorite color, but I didn't know how to say most of them, so
okay.
Didn't want to embarrass myself.
All right. Okay, that's, it's fair enough. Okay, so this isn't a science question, but I just want to let you know that we were just in the chat talking about potential names for JWST to save syllables. So we have some suggestions if you want to hear them. The first one is JWST, where you pronounce the acronym. We've got James, we've got J-Dubs, J-Money, Webby, J-Whoop. Anyways.
I'm partial to Janeway Space Telescope. I know that's not saving syllables, but it's my favorite Star Trek captain, so that's my favorite acronym.
Okay. Where would the best place for our viewers to find where would the best place be for our viewers to find up-to-date news on the launch date of JWST?
Probably, I'm sure NASA has like a press release site, but the NASA Twitter account has been where I've seen all of the launch updates, and that's where I would expect to find it tomorrow.
I guess also if you follow any astronomers, they'll be tweeting about it.
Yes, maybe melting into a puddle remains to be seen.
Do you feel like it is interesting how much astronomy is happening on Twitter?
Yeah, I mean, it's definitely kind of exploded over the past couple of years, and I don't know if that's partially because of the pandemic. But there's a ton of outreach and networking that happens on there. I personally enjoy it. I love when people put detailed threads about their papers, so I can read the thread and not have to read the paper if I don't have time. But yeah, I've met a ton of astronomers that way. I love it.
Okay. The first question from the chat is from Mars Newman, and they asked, how sensitive would a telescope need to be in order to detect biosignatures?
It's a great question, and I skipped over the slide on that because I was running overtime, I think. So the typical size of a biosignature in a atmosphere of a planet like, we'll say TRAPPIST-1e, which is one of the planets in this nearby system, is about 10 parts per million. So what that's like is a single grain of rice in a 5-pound bag of rice. One of those is the biosignature. So if you have a grain of rice and one of them's a different color, and you're not wearing your glasses and you're trying to dig through the bag to find that single grain of rice, that is what it's like to find a biosignature. So JWST is expected to have a what's called a noise floor. So basically the data can't get any more precise than 10 parts per million. So that means we're the uncertainty on our biosignature detection is going to be the same size as our biosignature detection. So it's hard to say if anything actually is a biosignature or if it's just noise.
Okay. The next question is from Stephanie J.H. Depp. Hopefully I pronounced that right. It's a very important question. Are there any sidereal stickers on the rocket?
Yeah, so Stephanie and I went to undergrad together, and then she was at University of Michigan at the same time in the physics department as me. There are not, maybe for Habwar-Lubex, this Habex-Lubar mashup, we'll get some on the rocket. But I am looking to, you know, how do I apply to be the person that puts these stickers on the rocket?
Up there with the rubbing alcohol, cleaning it off, and sticking them. Okay, the next question is from Jonas, I think that's Jonas. What kind of instruments does JWST have on it?
So there's two main types of instruments and detectors. There's instruments that'll take pictures. So I think most of them you're going to be able to take pictures with. But the main type of science that will be done with these instruments is spectroscopy. So breaking up all of the light that we get into the individual wavelengths or colors so that we can use that to determine what an object is made out of. So there's, I should know this, 3 or 4 instruments. I should know. I'm only planning to use like 1 or 2 of them. So I just pretend the others don't exist. 3 or 4 instruments. Yeah.
Fair enough. I wanted to ask you, how long is so like when we talk to telescopes, it takes some time to get the signal to the telescope. How long is that delay time to L2?
That's a great question. So it can't be more than a minute or so because the travel time to the sun is 8 minutes and it's nowhere near as far away as the sun. So I would say a minute or 2 at most.
Okay.
Which, not bad.
Probably like the times that you would be taking an exposure would be like a lot longer than sort of where that would be an issue for you, I guess. Does that make sense?
Yeah, so the telescope will have recorded exactly what time it started taking the data. So then when we get the data back down on Earth, we'll know exactly what time the telescope started taking the data, even if we didn't get it right away.
Alrighty. I think that is all the questions that we have and all the questions that we have time for, but thank you very much for a fantastic talk. And thank you as well to Alex for also a wonderful talk. So thank you again to both of you for volunteering to come talk to us. We know you're both very busy, so we're thankful for that. I also want to shout out our 2 streamers who work behind the scenes, Allie and Alex. They work really hard to put this on for us, and they do a great job every month. So before we head out, just a few last minute things I want to mention. If you are watching us asynchronously and not live, do please feel free to still interact with us. Subscribe to our channel to get notifications for our next show, and be sure to like this video so that more people can see it. Keep an eye on our Facebook, Instagram, and Twitter. We post about all of our events as soon as we have information on them. And we will see you here on YouTube next month, where we'll have 2 more lovely speakers for all of you.